In today's video, we're going to be looking at the concept of matter. How would you define matter? Matter is anything that has mass and occupies space. Matter is anything that has mass and occupies space. Now, let's look at the definition of things. Let's explain what a mass is. What is mass? Now, mass is the amount of substance in a matter. Now, let's look at our definition again. The matter is anything that has mass and occupies space. If you look around you, you're going to see that we have a lot of objects, a lot of things that you can see around you that are visible. As long as they are on Earth and they are occupying space, they are referred to as what? As matter. You yourself, you are a matter, right? And then look at the things around you. This marker I'm holding, the houses around you, the cars you're seeing around you. It has mass, it has an amount, it has a particular weight. If it is being weighed, it has a particular weight, and then the composition is what we refer to as what? As mass. Now, let's look at the three states in which matter exists. Therefore, matter exists in three states. We have liquid, solid, and what? And gas. Take for instance the water that you drink. Now, we can have this water in three forms. And then we have what? That's the liquid state, that is the water you drink. We have the gaseous state, that is the steam. And then we have what? The solid state, that is the ice. Now, let's break them down and then let us explain them extensively. Let's begin with the solid, and then let's look at the features or the characteristics of matter in a solid state. Now let's take our eyes, for instance. You're going to notice that our eyes has a fixed shape. It has a fixed shape, right, and a fixed volume. Now, if let's assume you go back from, let's say, from your workplace in the afternoon, and then of course you know that it's going to be the sun is going to be scorching, and then you go to your refrigerator, and then you find what you get a cold water to drink. But then let's assume that you didn't there was power supply, there was enough power supply to make sure the water is solidified. And now what are you going to do? You'll be able to take that water again, right? Because it is in a solid state, it is rigid, and then you can't drink it. So now we notice that it is what's in a fixed shape, and then that's a fixed volume. And then what did you notice about that's your eyes? What you're going to notice is that it's going to take the form of that container. If your container is like this, now, and then you put it like this, in the initial state, it has water filled in it. Now, if it enters your refrigerator, what is going to happen? It's going to be what? Solid. It's going to maintain the shape. It's going to maintain the shape of that container, such that if it is being removed, it's going to have the exact shape the container has. So, what can we do for this? We have fixed shape and what? And volume. Hope you're following. Now, another thing we can see is what? It is incompressible. You cannot compress it. Why? Because it is solid. You cannot compress that ice because it is what? It is solid. Now, another thing you cannot compress that is an example of a solid is what? Is your stone. Can you compress stone? No, you cannot compress it. So that makes it the second one. For solid, it is what? It is incompressible. Now, another one is that it has strong intermolecular force. What does this mean? It means that the force of attraction between this solid, this particular solid, your eyes, is what? It is strong. It is very strong. That is why you cannot compress it. It is very, very strong. They are tightly packed. Right? Now, we have the particle arrangement. For the particle arrangement, the particles are tightly packed in a regular pattern with minimal movement. That is, at a particular point, it is fixed, right? But then they will be vibrating at the point. The intermolecular forces are what? Are tightly packed. They are together. They are formed to become one. So they'll be vibrating at a particular spot. Another example that we also have, or other examples we have your bricks, we have metal, we have wood, etc. So they have fixed shape and volume, they are incompressible, and what? They have strong intermolecular the intermolecular force of attraction between a solid is what? Is very, very strong. That is why they are rigid. Now, another state we have is what? Is liquid. Now, for liquid also has a fixed volume, but no fixed shape. It does not have a fixed shape. Liquids don't have a fixed shape. And what does this do also? Similar to solid, it takes the shape of that container, right? It takes the shape of what? Of the container, of that cup, of that bottle, of that keg, or whatever. It takes that shape. So that's a fixed volume, but it has no fixed shape. Another one that we have is what? It is nearly incompressible. Can you compress liquids? No, you cannot compress them. You can't compress them. It's going to take the shape of that container. So now, what I mean by compression is going to be explained when we are dealing with gas. So now let's look at the particle arrangement. Now, the particle arrangement are less tightly packed than solids. And don't forget that liquids, they do what? They flow. But then the particles are what? They are weaker compared to that of solids. For that of solid, I explained that what? They are very tight. They are very tight. They are together. They stick together as one. But then that of liquid is a bit loose. Okay, it's a bit loose. Now, our examples, we have what? We have your milk, we have water, you have your milk, you have what else again? We have oil, etc. Now, let's look at our gas. Now, gas. Now, don't forget earlier I said that we have three states of matter. I said we have liquid, we have solid, we have liquid, and what? We have gas, right? Now, and this water that we are using as a case study can exist in these three forms. For the gas, that is when you boil your water. And what is going to happen? You're going to notice that the particles, when they are subjected to high temperature, they begin to escape. They begin to escape. And now you're going to see some things moving up around you, and then some people call it smoke, but it is not smoke. It is what? It is referred to as vapor, as steam. So now, for this gas, the properties we have no fixed shape, and no nor volume. It does not have a fixed shape, neither does it have a fixed volume. That is, they'll be moving around. It is non-regulated. It doesn't move. It's still moving. In fact, if you try to blow air to towards them, what's going to happen? They will just move in the direction of that wind. You understand what I'm saying now? Now, so they are highly compressible. That is why when you go out to the gas station to fill your gas, you hear some sounds because that it is fixed. It is it can be compressed. The same thing is when you go and meet your organizer to have your tire went flat and then you needed it to pump it up. What's going to happen? You're going to notice that they will start putting air inside it and then it will start increasing. So now, we can compress it. It can be compressible. And then, let me write it down. It is highly compressible. And then it fills the container completely. It's going to fill that your cylinder. It's going to fill it completely. That is why you can say, you can tell the person that wants to fill your gas that, okay, I want to fill my gas. How many kg is your gas? 5 kg. They can fill that exact 5 kg for you because it's going to occupy the whole space in your cylinder. Now, let's look at the evidence of the particle nature of matter. So now I'm going to be giving us two. We have Brownian motion experiment, and then we have kinetic theory of matter. Brownian motion experiment movement and the kinetic theory of matter. Now, let's take a look at Brownian motion experiment. You know that we have something called motion here. And what is motion? Motion has to do with what? With movement. Now, what does this experiment say? Now, in 1827, it was observed by Robert Brown that particles of pollen in water moved randomly due to what? The collision of water with the molecules. Now, pollen grains were dispersed in water. So what is going to happen to them? They will start to move. They will start to move in the direction of the flow of that water. They will continue to move. They will continue to move in that direction. As they are colliding with the water particles, they begin to move from one place to another. And then he also confirmed that matter is made up of tiny and constantly moving particles, like I explained earlier, that an atom is the smallest indivisible particle of an element. So it's the smallest indivisible. An example is when we have a chalk, like I explained earlier, that a chalk on its own is whole. I can decide to break this like this, break this, break this, break this, break this, break this. And then a time I won't be able to break it any further, right? Now, for instance, you have your powder. Our ladies love to use powder. Now, or foundation or whatever it is. You just notice that it is fine. When you touch it, it is fine. Very, very, very fine. And then a time is going to come that the least of it is what is called an atom. Because that's the one that makes up what we now refer to as what? As matter. Now, those tiny substances, when they come together, is what gives us what we know as our chalk. Now, don't forget, when I explained the Brownian motion experiment in 1827, they confirmed that matter is made up of tiny, constantly moving particles. It is tiny, but then it is in motion. Now, let me write it here. Now, from here, we can deduce that molecules will do what? Molecules exist. And also, the molecules are constantly in motion. Now, let's look at the other evidence, which is what? Kinetic theory of matter. Let me call this A and this B. Now, this explained that every substance is composed of a very large number of particles called molecules. Now, it is made up of what? Large numbers of small particles called molecules. Now, how would you define? Now, it also states that matter is composed of particles in constant motion with energy and spacing of particles determining the state of matter. And what does this mean? Now, from this we can deduce that molecules are also in rapid motion. They are also moving, because here we have kinetic, which means that they gain a particular energy and then they're going to be in what? They're going to be in motion. Our particles will be in motion. So, number one, we can deduce from this theory that molecules, similar to this, are also in constant. I hope you're following. Now, another one, we can deduce also that matter is made up of molecules. Matter is made up of molecules. Also, we can deduce that molecules are attracted to one another. Molecules are attracted to one another. So these are our deductions from the evidences that we have. The two evidences that I wrote here. Number one, I talked about Brownian motion experiment, and the second one, we talked about kinetic theory of matter. So if you are being asked, you should be able to answer those questions. Now, let's look at the application of kinetic theory of matter, because we need to know how we can apply them. Now, how do we apply them? Now, for the states of matter, I mentioned three. Now, for the first one, which is what? Solid. Now, it has low kinetic energy. Now, for what I'm doing now is similar to what we did earlier, but then I also be emphasizing some key points. Now, the first one we have here for solid is what? Low kinetic. Low kinetic energy. That is, like I mentioned earlier, that they are on a particular spot. They cannot move. They can only be vibrating in a particular spot because they possess low kinetic energy. They cannot move, but then they can only vibrate on a particular spot. Another one is strong intermolecular force. Now, this strong intermolecular force keeps them at a particular spot. It keeps them at the spot that makes them to what? To vibrate on a particular spot. So they won't move. They don't have the ability to move. But then, if you look at liquids, they have moderate kinetic energy, which is what? In between. Moderate kinetic energy. This is better compared to that of solids. You know, I said solids cannot move at all. They can only vibrate at a particular spot. But then for liquids, they can make that attempt to move. They can move, right? And don't forget that I told you some examples of liquids that we have. I told you water, I told you milk, and I told you oil. So they can move, right? And then we have another one, which is what? Moderate kinetic energy allows particles to move while remaining close. Now, for gases, these ones move at a very high speed. They possess a very high kinetic energy. That is, they can move. They can move. Now, so we have high kinetic energy. Now, let's look at another concept under the application. Let's look at evaporation and boiling. Evaporation and boiling. Molecules at the surface gain enough energy to escape as vapor occurring at any temperature or at a very high temperature. They gain more kinetic energy because they are subjected to what? To heat. So what is going to happen? They'll be looking for a way to escape. That is why if you have a bucket of water and then during the day and then you place it outside, what is going to happen? There's going to be a reduction because those molecules have been heated up, right? They have been heated up and then they want to escape. The same thing when you are boiling your water. Let's assume you are boiling your water at 100 degrees Celsius and then you forgot it. You forgot it there. You forgot to check it up. What is going to happen? You're going to notice that your pot is going to be empty because those molecules must have escaped into the atmosphere. And then they escape as what? As vapor. Doesn't as if any magic happened. Because they have gained enough energy. They will be in motion. Don't forget that at first now let's assume let's take this example. You have your pot here, and then you have this is your pot. And then you have it filled up with water. Now, let's assume that it is not even water. Let's call this solid. Now, let's assume you have this. Let's say you kept a particular soup inside the freezer, and then it must have become solid, right? What is going to happen? And then we're like, okay, you need to eat a particular. Let's say you want to eat amala. And egusi. Let's assume this is egusi, right? Now, and then it has solidified. So you want to eat this up so you can be able to eat your amala and egusi. Now you place that cold egusi inside your pot, and then you subjected it to it, and then you lit it up. What is going to happen? At some point, let's say at the initial state, the solid is going to remain there. It will be vibrating. It will vibrate like I explained. But because we brought it out, in fact, just by removing it from its original atmosphere, original temperature, what's going to happen? It will begin to lose some energy. It begins to lose some energy, and then you begin to look for a way to what? To move. You begin to look for a way to move. Now, what's going to happen? So, if you now subject this thing to heat, you're going to notice that it is going to be melting. It will be melting. Or even if it is just ordinary water or ice that is inside this pot, it will be melting. It will be melting. The time it's going to come, that it's going to turn to liquid. The time it's going to come, that it's going to turn to what? To vapor. If you're not careful, if you have your ice here and you didn't check it for over a period of time, what's going to happen? It's going to escape. And then when you open your pot, it's going to be empty. Now, so let's look at the concepts, another concept, under the application of kinetic theory of matter. All these topics are very, very key. So we have cohesion. and what? Adhesion. So, how would you define cohesion? Cohesion is the attraction between particles. Is the attraction between them, the force that binds them together. Like I explained, that of solid, that they are together. They are bounded together, right? Now, cohesion is what? The attraction between particles, like particles. Now, examples. We have water molecules. Now, let's look at adhesion. An example, or what this means is the attraction between unlike particles. E.g., we have water and glass. What is going to happen here? You see that the water will just stick to the glass. Okay, they are unlike particles. So this is what? This is adhesion, this is cohesion, and this is adhesion. Now let's look at crystalline and amorphous substances. Now, we have under this, we have two of them. We have crystalline solids, and then we have amorphous solids. Under the atomic arrangement, I'll talk about the atomic arrangement now. So, let's look at crystalline. Now, in these materials, atoms or molecules are organized in an orderly manner, repeating three-dimensional lattice structure. What do I mean by this? Now, all these solids, they are organized. They are in an orderly manner. Let me give you an example. This is a perfect example of a crystalline solid. This is a perfect example of a crystalline solid because they are arranged in an orderly manner. Another example that we have is when a bricklayer is actually laying blocks. He's laying blocks. You're going to notice that they don't just do it like this. They don't lay blocks like this. What is going to happen if they lay blocks like this? What is going to happen? It is going to what? It's going to fall. That is why if bricklayers are laying blocks, they lay it like this. And it's going to follow that manner. Something like this. So it's going to follow that manner. If it's arranged like this, it's not going to fall. It's going to be organized. So don't forget that I said that crystalline solids, they are what? They are highly ordered. They are highly organized. And then now, an example that we have. Let me erase this. Cameraman. Let me just start. I'm going. Okay. Highly organized. Repeating. Three-dimensional lattice structure. So let me erase this off. Don't forget the example I shared about our bricklayers. When they're laying their blocks, it is always arranged in an orderly manner. It is always orderly. Now, the other one that we have is what? Amorphous. Oh, I forgot. An example of this is what? The salt. The perfect example is what? Is salt, sodium chloride. Now, for amorphous substances or solids, now these solids lack a long range order in the arrangement of their particles. What does this mean? They are not organized, right? They are not organized in their manner. Now, from the word amorphous, it means without shape. It does not have shape. It is not organized. This is disoriented. Now, an example of this, or let me just put this down. Solids. No shape. So, examples of these, we have glass, and plastics. Now, let's look at the physical properties of these two. Physical properties. Now, the first one we're considering is what? Melting point. Now, crystalline solids, they possess sharp melting point due to their organized structure. Because they're organized, they have a high tendency of melting quickly. So it's not going to give the heat too much problem. The air is going to melt quickly, it's going to melt fast. Now, unlike amorphous substances, they soften over a range of temperature. So they lack a precise melting point because they're not organized. So they lack a precise melting point. Now, so for amorphous, substances, or I mentioned sharp melting point. So, but for this is crystalline. So for amorphous substances have no precise because they melt over a wide range of temperature. Because they melt over a wide range of temperature. Now, let's look at mechanical properties. So now, mechanical properties. Crystalline materials are typically rigid and brittle. They are typically more rigid and brittle. Are you following? They are typically more rigid and brittle. But for amorphous solids, they tend to bend to be more flexible and be fractured in irregular manner. Now, for something to be rigid and to be brittle at the same time, you should know that it is when they ask you that a substance that is rigid and brittle, that substance is called what? The crystalline substance, right? So now, but for amorphous solids, they tend to be more flexible and be fractured in an irregular manner. So for amorphous substances or solids, we're looking at the mechanical properties, that is the physical properties of the amorphous solids or substance. Why crystalline solids are rigid and brittle. Why crystalline solids are rigid and